Okay, so what was it that gave us trouble here? Well, in this case, we weren't told the derivative. We had to figure out the derivative. And the mistake that we made at first was just plugging in the expression for b. But we don't want the expression for b here. We want the derivative for b. Again, the one thing we wouldn't want to do is just plug in a number for b. We want to plug in the expression for b and then take its derivative, because we can't take the derivative of a number. Make sense? Okay. All right, so those are a couple of key cases. All right, so here we have a problem where we have some stationary rails and a movable rod. And the rod is moving to the left at 5 meters per second. All of these can conduct electricity, so there's the potential for having electricity moving through here. This has a length of 4 meters. We have a uniform magnetic field coming out of the board of 3 Tesla, and the magnetic field exists everywhere. And again, we want to find the magnitude and direction of the induced current. Let's try to use the same kind of systematic approach that we used before to attack this. So how would we get started here?
Okay, so we write the equation for induced, for magnetic flux.
Right. Good.
And simplify it.
Good. Yeah, what would that simplify to?
To be BA.
Right. Once again, the component of the magnetic field that's perpendicular to the surface is just the entire magnetic field. So again, this will simplify. And we can take this out of the integral because it's constant. Okay, so that gives us this expression. Good.
Okay. And then we take the derivative of that.
Okay. Well, we can try working this out on paper.
And then it looks like the magnetic field is a constant, so we can pull it out.
It's good that you started with the general expression. Well, we have the magnetic field. In this case, the magnetic field is constant in both space and time. Yeah, in this case, it's constant in both space and time. So we can take that out. That's good. Good.
And then we can find an expression for dA dt.
Right.
So we have a length of 4 meters.
Mm-hmm.
I'm not really sure.
Okay. Well, the reason we're having some difficulty here is maybe we haven't done as much work as we need for the first step. Remember, the first step is to get an algebraic expression. Well, in this case, we need an algebraic expression for the area. We can't take its derivative without an algebraic expression. But what's a general expression for how to find area?
Length times width.
Good. Now, in this particular problem, which of these is a function of time, the length or the width?
The width.
Yeah, depending on how you define them. But if we call this the length, and this the width, so it helps to say who's being a function of time here. This is a constant, and this is the width. So we can go ahead and plug in, the length is just 4 meters. We can go ahead and plug that in because that's not changing. All right, now we need to take the derivative of the area. Well, that would be the derivative of this. Well, how can we, what's the first thing we can do to simplify this?
Pull out the 4.
Right. All right, and now we've got to have a number to plug in for the derivative of the width with respect to time. Well, can you see any information they gave us that would allow us to figure out this derivative? Let's take a look at all the information we were given in the problem. There's some information here that would tell us the rate
that the width is changing by 5 meters per second.
Yeah. So what is the derivative of the width with with respect to time?
5.
Yeah, that's right. Technically -5, but we're not trying to get signs here, just directions. Something that might help here is to think about the units. What are the units for width?
Meters.
And what are the units for time?
Second.
So we might just check the information we were given for something in meters per second. And here's the information we were given in meters per second. But also it should just be intuitive that if we're moving to the left at 5 meters per second, that does tell us how fast the width is changing. The derivative of the width tells us how fast the width is changing. Well, this tells us that exact information. All right. So this would then be 4 times 5, or 20. Well, that's the main thing I wanted to go over here that gives people difficulty. Notice that once again, we don't need to know the level of the area. We never told you what the actual width was. We want an expression for the area, because only with an expression can we take the derivative. And the reason we were having trouble with this at first is we were trying to take the derivative before we'd gotten an expression for the area. First you need an expression, and only then can you take the derivative. All right, so plugging in here, we know that we can plug in 3 Tesla for B. And what are we going to plug in for the derivative of the area?
20.
So this comes out to be 60. Okay, good. So let's finish off the problem.
Okay, so now that we've found the change in flux, we know that that's equal to the induced voltage.
That tells us the magnitude of the induced voltage will be 60 volts. Good.
And then we can use V equals I times R to solve. That's 60 divided by what was the 60 divided by 2 is 30. Yeah.
That's our resistance. So that would give us a current. Did you put it in the wrong units? What's wrong? 30 amps. Good.
Okay, so now we know the magnitude and we need to find the direction.
Right.
So we know that the magnetic field is coming out of the board. And let's see. And I think as the area is decreasing, the magnetic flux is going to decrease.
Good. That's our step 1 for Lenz's law. Step 1 is to determine the change in the magnetic flux. Well, if the loop contains less area, then it's going to be less flux going through it. So that's our step 1. Good.
And so we know that the induced magnetic field is going to oppose that.
Right.
So it's going to be coming out of the board.
This is already coming out of the board, but there's going to be less and less flux coming out of the board. We want to go back to having more flux out of the board. All right, or you can just use the mechanical rule in this part of the handout. When the flux is decreasing, the induced magnetic field should be in the same direction as the external magnetic field. Okay, good.
So now, if we go to maybe the top of the wire, let's say, and we look at the induced field below it.
So I should have written that down. We just figured out that the induced field looks like this. Good.
Then we know that the current's moving to the left.
So I want to put my thumb above my fingers, and I want my finger pads to be pointing into the page. My thumb is up here, above my finger.
Out of the page, right?
You're right. Let's try again. My thumb should be up here, and the finger should be below there, pointing out of the page to represent the induced field. So what direction is the current in?
To the left.
Good. So what's the answer to the question?
So the current is 30 amps moving to the left.
Right. Except it's only moving to the left up here, so it would be better to say whether it's clockwise or
counterclockwise.
Yeah, counterclockwise. 30 amps in a counterclockwise direction. And if they told us that counterclockwise was the positive direction, then we could say the induced voltage was positive. Or if they told us that counterclockwise was the negative direction, we could say the induced voltage was negative. A lot of the time they wouldn't ask for that. Okay, good. So I would recommend actually writing down these steps here for Lenz's law, because it's easy to get confused about that.